Alright, back with video problem number 5. For this one, we're back thinking about Old Man Gauss. So if you need a refresher, go check video problem 1. We have our vectors describing movement by the hoverboard and the magic carpet. Now we know that we can use this to represent a new basis in R2. And here it just states that, in this new basis, Gauss lives at 3017. And we have a few different parts of this problems. So let's just go ahead and start off with part A. Part A says Uncle Kramer in the standard basis lives at the location 2571, and we want to express this in the beta basis. So one of the first things that we can do is define our transformation matrix, which is where we take the columns. So V1, we take V1, take V2, and we insert them in our matrix. And now this will map our standard base vectors 1, 0, and 0, 1 into our new coordinate system. So if we take the inverse of that matrix, given by this formula right here, we can take vectors that are in, A inverse applied to a standard base vector will give us a vector in our new beta coordinate system. So this right here just shows that multiplication process, and this is Old Man Kramer's house as represented in the new basis. Part B says that in our new basis, consisting of the 3, 1, and 1, 2 vector, our coordinates are given by 8, 3. So we can apply A and do this matrix multiplication again, because if we apply A to a vector that is in our beta basis, we get our standard. So this is in the beta, and then the output is alpha in the standard coordinate system. So if we think about this geometrically, we take 8, that is this 8 right here, we take 8 steps in the 3, 1 direction, and we take 3 steps in the 1, 2 direction. So down here I've kind of highlighted, this is the 3, 1 vector. So we have 8 of these and stack them all on top of each other. We will be somewhere out in this direction. And similarly with the 1, 2 vector, we just take 3 steps in the 1, 2 direction. So this is our 1, 2 vector, and we take 3 of those. So it's easier to think, the linear combination makes this easier to think about geometrically. So 8 steps in that direction, 3 steps in the second direction will give us our standard coordinate representation, and that ends up being 2712. For part C, we just want to change some vectors in the standard basis into our new basis. So we know that matrix multiplication, if we multiply by the inverse of A, we will have our beta representation. So we just do that matrix multiplication and we get these final results. 7, -1 in the standard basis correlates with 3, -2 in the beta the beta basis, and -6, 3 correlates with -3, 3. And again, now we are going to think about changing our beta representation to our standard base vectors, just using a linear combination, the same geometric reasoning we used earlier. So 7, -1 just tells us we take 7 steps in 3, 1 and -1 steps in the 1, 2 direction. So execute this math, we get our final answer of 25 in base coordinates, and similar -6 steps in the 3, 1 direction, 3 steps in the 1, 2 direction, and we end up at -15, 0 in the standard coordinate system. So here we've shown, thinking about linear combinations of just taking steps in certain directions, much like we initially thought about with linear combinations at the beginning of the class, but now instead of just the normal 1001 base vectors, we have more complicated, more intricate base vectors that are actually make it easier to analyze complex systems. So, shown matrix multiplication, some geometric insight, and